So next, we'll be joined by Jerome Kieffer talking about GPU acceleration of HDF5.
So hello, I'm Jerome Kieffer, and I will speak to you about processing HDF5 data using GPUs and multithreading. So the outlook of the talk is I'll present you some profiling of a typical data reduction workflow, and yeah, if it can be multi-threaded. So the issue has been raised by Elena. It has been Francesc spoke about multi-threading. This is apparently a big issue. And I'll also speak about offloading the processing to GPUs. And yeah, a final word about compression. And yeah, sorry for those who are in the auditorium. Well, this whole story came from a phone call from Marco Camarata last year, who told me, well, we like the software you are doing, Pi5 for those who don't know it. It usually works very efficiently, but I have the feeling that it's pretty slow. Could you please help us and provide us with a tutorial on how to make processing of data fast? Because I have the feeling that it's not. And well, the typical workflow I choose, and it's representative from what Marco is trying to do and many other scientists at ESRF, is, well, basically ESRF purchased quite a large number of new detectors for the EBS source. So we have 12 new detectors, and those detectors are built by detectors. They are working nicely, and they produce HDF5 file, and those HDF5 file contains data stored in bitshuffle LZ4 compression scheme. So for the whole presentation, I will speak about HDF5 file, but those file contains data compressed in bitshuffle LZ4 data format. Sorry. Yeah, all what I'm presenting is available from this web page, which is part of the documentation of Pi5. So this file usually contains a stack of images that I represent like this. And this stack of images is usually processed with a piece of software. I took Pi5 because I'm writing it, but it could be something else to generate a set of vectors that are stacked and again saved into a new HDF5 file. So that's the typical workflow we will investigate and try to find why it's slow. So inside the HDF5 library, there's a lock that prevents multi-threading. So let's say that the reading is pure IO and serial, and it's enforced by the lock inside the HDF5 library. And the bitshuffle LZ4 is parallelized, so the decompression can be made multi-threaded using OpenMP. Pi5 itself is parallelized using either OpenMP or OpenCL. And then the writing to the new HDF5 file is parallel for the compression part, and for the IO part, it is serial, again, because of the HDF5 library. So I took the latest computer we had at that time, so it was last year. So it's 32 cores, well, 2 times 32 cores AMD high-end server. And I took Eiger 4M images and a bunch of 4,000 images just to have something representative. The data are containing purely synthetic data that represents some Sachs curve of Gunier-shaped data. Well, synthetic data with representative noise and so on and so forth. So the storage is in HDF5 with bitshuffle LZ4. And I do the azimuthal integration of this using 1,000 bins. And those are the performances. And if I looked at the performances, having everything in parallel, so 2 times 32 cores, for the processing, I get 5 frames per second. So that's not exciting. The reading, 170 frames per second. And what if I disable the parallelism completely with an OpenMP, OMP, num threads equal 1, I get much better results. So either you use one core, 1/64th of a computer, and you get 5 times faster than using the complete computer. And I guarantee you the complete computer was busy doing things, but not efficiently. So multi-threading might look nice, but it's not the ultimate solution because you can get worse performances than just doing serial code. So what's going on? What's going wrong? So the computer is has 2 NUMA nodes. So this is the output of LS topo. So we see 2 green boxes here and here. So those are 2 NUMA nodes. Each one has its own memory subsystem, and there are some mechanism for exchanging data from one to the other. And this communication is very slow, and it's much worse on AMD platform than on Intel platform. Those are both x86, but they have completely different behavior when it comes to multi-threading. So what I decided is to take one block. Here we have a level 3 cache. I decided to reduce my set of working to just one block, so 4 cores. And this is the result I obtained. So the reading is three times faster. The processing is much better than previously, and overall, I'm better than previously. So knowing one's computer, one's platform is of key importance. And well, of course, if I take a new Intel server, I will get different bottlenecks. I will get a different layout like this, and I will need to find another solution. So I promised Marco to find him a solution to get his processing done quickly. So I did a benchmark on 2 computers, the previous AMD server and my workstation, because it's the computer with which I'm working every day. So my workstation is from 2016. And if we look at the performances of Pi-Phi, if we start with a single core histogram algorithm, that's the orange curve here. If I go parallel, so parallel is the dashed line. It's here, it's in red, and we see a clear increase of speed when we go parallel. If I use the GPU inside the same computer, I'm much faster. But now if I take the AMD server, so the speed in single core, it's the violet, it's this curve. So it's not very different from my computer, but at the end, the cores are clocked more or less at the same rate. So the fact that the results are similar, it's not really surprising. If I use the sparse matrix multiplication implementation, which is serial, but uses already the sparse matrix representation, is as fast as the 6 cores of my old workstation. But when I switch on the parallelism, we see that the performances are going really bad. So this is, as I said, something typical from the AMD layout of the processors, which basically comes down to saying that having small OpenMP jobs is really bad. So many cores computers do not play very well with OpenMP. So I'm sorry for no, it appears somewhere else. Yeah, so much better. Yeah, but that's not much problem. So one problem is that memory transfer is usually a blocking factor. So in our processing, we read data. So next, yeah, we do some I/O. So this is serial. So one single thread. Then we decompress. at the end of the decompression, we wait, we have a synchronization barrier. Then we have another processing that is parallel, also parallel, another synchronization barrier. And this overall makes it fairly inefficient. So one of the solution is to work more and to chat less, so having less barriers. So the idea is to build a pipeline that would decompress on one thread and integrate within the same thread, the same image, and then have several threads doing the same thing and having one worker that would do the I/O and feed the data to the decompressor and the complete pipeline. Yeah, if some of you know about Python, I'm coding in Python, and once you start to do some processing in Python, you probably heard about the Python global interpreter lock. And so the Python global interpreter lock prevents you from doing anything multi-threaded. So this should not work in theory, but in practice we will see that it does, because we are not working at the Python level but underneath. So to start, I've started to analyze what the pipeline is made of. So the first step is reading data. It's pure I/O, and I use so this part of the API, which is the direct chunk read from H5Py. And for this, we reach 3,000 frames per second. So I'd like to apologize to Thomas and John White, who's online, because I didn't use the new features I provided, which removes one mem copy. And so the figure you can get are actually higher than that. So 3,000 frames per second. Then you do the decompression. So if you enforce bit shuffle to work on a single thread, either by recompiling it, disabling OpenMP, or by saying OMP num thread equal 1, you get 240 frames per second. And then the integration. So we've seen, so if we use the CSR sparse matrix representation, which is inherently done for working in parallel, but we want it to run on a single core, we get 15 frames per second. But if we transpose the sparse matrix into a CSC matrix, we have a better memory layout, and we reach 20 frames per second. And if we put everything together in a simple pipeline, read, decompress, process, we get 22 frames per second. So we don't lose a lot. We are on the order of speed of the smallest of the slowest part of the pipeline. So now we can use Python thread pool, and what we see, if we increase the number of threads, so the computer has 64 threads, well, 64 cores, 2 times 32, and we see a nice linear scaling of the processing speed from 22 frames per second on a single thread up to 850 frames per second, around 40 or 45 cores used. And I guess what we see here, this plateau, is a plateau linked to the fact that we are hitting the GIL, so the Python global interpreter lock, but probably also the lock inside HDF5. But since HDF5 is less used than Python, it's more probably the GIL that we are hitting. So from this, we know that this number of threads we have here is really linked to the time spent for Python doing the management. And this means also that if we have a computer with, let's say, 500 cores, we will probably not be able to go much higher than that. So if the work we are doing is mostly GIL-free, we can use multi-threading in Python, and it works and it scales up to a certain level. So it works much better than OpenMP. The drawback is that we had to write something like 100 lines of code instead of the 10 lines needed to do the simple pipeline, and we have a scale up of about 40 times. Multiprocessing is one way to go above the global interpreter lock from Python, but then you will hit another problem, which is the serialization issue. So there are libraries for serialize any kind of Python objects, but the cost in the serialization and the transmission of data from one process to another, you will have to pay for it, and yeah, your mileage may vary. So I promised you to speak about GPUs. So for the processing, PyPhi is out for 10 years now. It has been published 2014 for the implementation of GPU processing. So that's not something new. Compression is something that is fairly recent. So in 2020, NVIDIA presented NVComp, which started as an open source project to do compression and decompression on NVIDIA GPUs. And since 2022, NVIDIA made it closed source, so it's no more open source. And of course, it's CUDA only. So I'd like to thank John Wright, who did some initial scratching on this side. And yeah, it's worth investigating. So last year, I spent a bit of time to implement the LZ4 decompression and the bit shuffling. This year, I worked on the LZ4 compression itself. I'll say a word. So for the processing azimuthal integration on GPU, so there are two algorithms that are possible, either histograms, so it's based on atomic operations, it's not very efficient. So the CSR sparse matrix multiplication is very well suited. We can reach 1,500 frames per second, and it's limited by the PCI Express bus. And we have implementation of error propagation using different error models. And this is something quite unique to PyPhi today. And we also have double precision, which is emulated using two floats in PyPhi, which is also something we can guarantee a level of precision of 56 bits per word. So if we look at the profiling, so in a GPU, the processing is done small chunks by small chunks, and each chunk is called a kernel, and each kernel we can measure and profile its runtime. So for example, a typical processing of PyPhi, so here it takes 2.7 milliseconds from the Python timeit command. 2.2 milliseconds were spent inside the OpenCL, so on the GPU. We see that most of the time is spent on sending the data from the host to the device. And then we convert the data to float, we reset some arrays, we perform some correction. The azimuthal integration itself is here. It takes 0.4 milliseconds, and then we retrieve the data. The computer is my old workstation, which is still PCI Express 3, and the GPU is limited. So with a newer computer, we could see this timing, so 1.5 milliseconds, to go down to here, 0.7. It would make the processing substantially faster. The fact is that for now, transferring the data is 4 times more expensive than the critical part, which is performing the azimuthal integration. And it would be great if we could perform the decompression on the GPU. We would have fewer data to transfer and a better GPU utilization. So I wrote a set of kernels to perform the LZ4 decompression. So here we send the data to the GPU. Then we have to read all those data to find where the different segments in LZ4 are located. So this is what takes most of the time. And once we know where every segment is, either we copy the data from one part, either we copy the data from some other part. Well, things that GPU are very good at, and this takes 0.2 milliseconds for a frame. And yeah, it includes bit shuffling because this is done for free. So technically speaking, if I compare the 6 cores of my old Xeon, we get close to 1,000 frames per second. The implementation I made does 800, 900 frames per second. So we are close to, but we are not extremely fast. So it's not super exciting. So now I put everything together. So I have small transfer because I send small data. Then I have the analysis of the LZ4 compressed block, the decompression, the integration. So this is fairly equilibrated. So if we wanted to have more kernels doing more work without big outlier, this is a success. So we reach 450 frames per second using, well, serial programming, let's say. And we could have multiple processes using the same GPU, and we get 500 to 600 frames per second with several workers. Again, the whole code is available here. And I said I'd like to conclude with the compression. So my algorithm, I'm not very happy with the compression algorithm I obtained, so I took the reference one from NVIDIA. And here we have the compression rate, decompression rate, and the decompression speed and the compression ratio obtained. And we compared this with the LZ4 implementation. I forgot the name of the author, but the standard one, the reference one. And what we see is that the compression rate is much lower for the implementation by NVIDIA, because they are cutting some corners to get it running faster. And so the compression ratio is 3 times lower than what is available on the CPU. The decompression speed we have seen, it's in par with what we obtain on CPU. And so basically NVIDIA achieves this, well, I'm achieving the same as NVIDIA, I would say. And for the compression ratio, we see the compression speed, it's much slower than what you obtain on one CPU thread. And to be fair and to be representative, I did bit shuffle the data beforehand so that we can compare the figures. So as a conclusion, the LZ4 algorithm is not very well suited to GPU, but with this bit shuffling, we compress a lot the data, so we can compensate a bit for this loss of speed. But so the GPU is not the final device for doing this kind of things. A word on power consumption. Well, I write code, but I'm also conscious that the directives I'm giving to scientists on how to process the data will influence the way they use compute resources. And so if I treat my data simply using my old workstation, so this has been benchmarked, it consumes less than 20 watts when, let's say, idle. And when I use the processor full power, it consumes 70 watts. And I can achieve at best 35 frames per second on it. Again, 4 megapixel, always the same. This gives me 2 joules consumed per frame. If I use wisely the HPC server, so this dual AMD EPYC, which reaches 850 frames per second, we are at 0.7 joule per frame. So we can do, let's say, 3 times better than a workstation when both are used in a wise manner. And if I use a GPU in my workstation, I get 0.5 joule per frame using one simple serial Python code, or 0.4 when I use 2 processes. This is just to give an idea. So we get a factor 4 to 5 improvement by using the proper device. So the GPU is consuming 145 watts when used with one process. And I didn't put the figure, it's something like 200 watts with 2 processes. So at the end, I'd like to thank some inspiring scientists, so Marco and John, and also all my very helpful colleagues, Thomas, who's in the audience, Armando, who's not here today, but also Pierre Paleo, Alejandro Holmes, and Samuel Debion, who have been working on the integration of serial crystallography, and we've worked a lot on compressing data. And I'd like also to thank the open source community around HDF5 and H5Pi, and then Thomas Quiver. And thank you for your attention. I'd be happy to answer some questions if you have.
Thanks. Do we have any questions? Okay.
Yeah, thanks for the nice talk, Jeremy. I wanted to ask about the HDF5 plugin, and that it is by default now switching OpenMP.
Yeah.
That you
It's switching
emphasize.
off OpenMP.
Yeah, yeah. So then when I, for example, load also import also NumPy, and I would like to use NumPy, and I would like to have OpenMP enabled, yeah, on like many cores. Does this interfere with HDF5 plugin or not?
Well, probably Thomas is the best person to answer, but I think I can, because NumPy will not use OpenMP by default, but some linear algebra, for example, linear algebra libraries you are using could be using OpenMP.
Yeah, yes, you are right. Yeah.
Thomas will correct me if I'm wrong, but I think at the building of the HDF5 plugin, it's OpenMP that is disabled completely. That means that it's not compiled with the OpenMP option, and it will be serial, and it will, so we will not have interference between OpenMP being disabled into the HDF5 plugin and some other pieces of code which could use OpenMP.
Okay.
So the way I've done it by saying OMP numthread equal 1, this would create an interference, but having it disabled at the compile time will allow you to use OpenMP if you wish, decide.
Okay, that replies my question.
Any other questions? If not, then I'd say, well, thank you again.